The chain rule is a very powerful derivative rule. It allows us to take the derivative of a complex function that is a combination of two individual functions that we know how to take the derivative of. Now here I've written two ways to think about this derivative. They mean the same thing, but for certain students, one way makes more sense than the other. So our function itself is a combination of two functions. So usually we see this as f of x, right? And instead we say this as f of g of x, which means the function f of x, wherever the x term shows up, we replace it with another function, some g or g of x you can call it. So this is essentially a substitution rule, right? So if I call g of x u, then I have a f of u, which is basically the same thing as f of x, right? So I can take a derivative of that, and that would be like dy du, right? But that's not taking the derivative of y with respect to x. That's taking the derivative of y with respect to u, this function u. So then I would need to multiply that by the derivative of g of x, or because I made the substitution, du dx. So you can think about it this way. For myself, this is the way that makes most sense to me. But the other way to look at it, which is essentially the same thing, is f gx, the derivative of this, is you take the derivative of the outer function, f prime, by plugging in g of x into the derivative form of it, and you multiply that by the derivative of g of x with respect to x. Right? So this is essentially dy du, that's essentially this term here. Du dx, that's essentially this term here. So the functional forms can be very confusing to students the first time you see it, but the example problems will make it a lot more clear. So we're going to show you some example problems. Sometimes graphs make sense. I'll show you the graphs. We'll try to make sense of them, try to reinforce why the chain rule works or that it does work. But sometimes the graphs are not that meaningful. But I'll show you all those graphs just so you have something to reference. Okay, so we'll start with a easy problem. ln, so natural log, e of x, the exponential to x, right? This is an easy problem because we can apply the chain rule to this form of it, but we know that the rule of logs, that natural log of the natural number to the x power is just going to be x. So I know the derivative of this without doing any work, right? I can just use the polynomial rule. This would be just equal to 1. But let's do the chain rule here, and let's show us that it can be equal to 1. So the first thing you do is you need to break up the function into its components so that you can either use this form or this form to build the full derivative. So what do we see? And you want to think about it in the context of the tools that we have, right? So that you can apply the chain rule, because you know you're going to need to solve for f prime and a g prime. So the inner function is my gx term or my u term. The outer function is my f term, right? So we can think about it from this perspective. So my inner g function is my e of x, as shown here. My outer function is natural log x. And we want to write it in terms of x and not in terms of g of x, because you want to be able to directly apply the tools that we already have, right? So if we graph these, we have x, or ln ex in red here. That's just the y equals x graph, the linear graph. And then we have natural log x, and then we have exponential e to x. Okay, so now the next thing we have to do is we need to solve for these derivatives. We need to find f prime and g prime, which I have right here. So g prime is just ex because of the exponential rule here. Derivative of natural log x, where's it? Right here, right? So just 1 over x. Now, when I combine them to the final form, I'll take g prime x, this term right here, and multiply by f prime gx. Right here it's f prime x. To make it f prime g of x, I substitute all the x components with g of x. Well, g of x is ex, so I substitute e of x in there. And when I do that, okay, so before I do that, I can also write it in this form. To write it in this form, your g of x term is your u. So this is essentially dy du, d natural log with respect to u, du, multiplied by du dx, right? And du, so u is e of x, so dex dx. And we plug that in either form, right? So if you look at it from this perspective here, this will be natural log u, derivative of that is just 1 over u. Derivative of e of x is e of x. And then substituting back ex is equal to u, so you get 1 over ex times ex. This is equal to 1. If you did it in this form here, 1 over x, you substitute that f prime x with a f prime g of x, as you saw here. So then you'll write in 1 over g of x. G of x is e of x right here, right? So then that'll be that same exact term there, and it'll be equal to 1. So if we graph these terms, we'll have the derivative of the full system in this dashed red line here. We have g prime as ex, and then 1 over x for f prime in green here. Not very meaningful graphs there, but this demonstrates, because I know the derivative of x is equal to 1, that the chain rule does work here. Okay, so let's take a look at another example. And then here's your ln natural log ex, which is just x, and then derivative of that, which is just equal to 1. All right, let's take a look at one more example. Okay, so e to the x cubed is our next example problem. The first step to using the chain rule is identifying the two functions we want to look at. So take a second, try to see if you can figure out what's my inner function and what's my outer function. Essentially, what's my f term and what's my g term or my u term, right? Think about what you would substitute for u to plug into this equation and get into a form that you know how to solve from this left column here. Okay, so I see an x cubed. That's a good indication that this is going to be one of my polynomials, or one of my terms. That's going to be my inner function, because it's e to that function. And then e to x would be my outer function, my f term. Okay? So I can substitute u for x cubed, and then e to x will be my outer function, or my e to u function. So we'll graph these terms, and then we get in red there is my e to x cubed. This blue line is my x cubed, my u substitution value, and then e to x is in green, which you kind of see here. All right, so what I need to do next is take the derivative of each of these. Derivative of x cubed is 3x squared. Derivative of e to x is just e to x. All right, so now that I have this form, I can do a couple things. I can either do a substitution for u, or for dy du, and basically treat this as f prime u, which would just be e to u, and then make the substitution back for the u as x cubed. Or I can think about it as f prime g of x, which is essentially the same thing. So whichever way makes more sense to you, go ahead and do that, right? So we can look at this as, right down here, dy du. dy du is basically df du. So e to the x, but basically e to the u in the substitution. That's your g of x substitution. And then du dx is essentially g prime. That's 3x squared, or your x cubed term. So we get eu, where u is x cubed, and derivative of x cubed with respect to x is just 3x squared. So 3x squared times e to the power x cubed. Okay, so there's my derivative. The derivative is in red, in the red dashed line here. There's my 3x squared in blue, and then in green is e to x again. And if I take a closer look at just the function Here's my e to x cubed, and the dashed line is my derivative, 3x squared e to the x cubed. At least visually, you can see that my function reaches somewhat of a looks like a zero slope there, and that matches up with that point there. We have it rising and then asymptoting. So the peak of that local should be somewhere in the middle here, and we see that reflected in the derivative as well. At least at a very minimal level, qualitatively, we can see that the graphs make some sense there. All right. So hopefully you see a pattern of how chain rule is applied, and I think doing more problems gives us a better sense of how this rule works, rather than just looking at the general definition here. So let's take a look at a couple more examples. Here's an interesting one. We have sine x squared. So again, which function is my g of x, or my u term, and which function is my f term? So hopefully this one's apparent to you. The outer function is my sine. The inner function is my x squared. So we'll define those. So I have u as x squared, or my g of x, and f of x will be my sine x. So I graph those. Here I have my x squared, or my u term. In green, I have my sine x. When we combine the two, right, the amplitude of this full function y is still just going to be between, the amplitude is going to be 1, but the peaks and troughs are going to be between -1 and +1. But what changes internally here, we remember from our trig videos, is the frequency, or the period, right? So the frequency is constantly changing as x, or the value in here is changing, right? It's growing in a quadratic manner, right? So the frequency is getting increasingly larger and larger, but the amplitude is staying the same, right? So let's think about how that would affect the derivative. So when we flesh out the final solution, I think you'll find some interesting properties show up, right? So we take the derivative of x squared, which is essentially the rate of change of the frequency term here, right? Then we could take derivative of sine x, right there, tells us it's cosine x. So let's do that. So I have 2x and cosine x. And then I can apply either this form or this form. So d sine u du is looking at this as dy du, where u is x squared, and then du dx is dx squared, because that's u, dx. So derivative of sine, we saw earlier, is cosine, so cosine u. So then I would need to substitute u with x squared, so cosine x squared times dx squared dx, which is just 2x. So the graph of this is interesting. So I have 2x times cosine x squared. So just like in the sine x squared term, the frequency constantly changes. In this one, cosine x squared, this section here, the frequency is constantly changing. It's you can kind of see it in the green line shown here, but you can really see it in the full derivative in red here. And then you see 2x, the amplitude of this final solution, the derivative solution, shown in the dashed blue line here. And you can see that it's basically enveloping, right? A negative 2x would envelope the amplitude, the peaks and troughs of your final solution. And it does make sense on a practical level, right? We can take a look here. So the dark red in the center part represents sine x squared. The growing, and these are dashed lines just to make a distinction, is this 2x cosine x squared. If we zoom in a little bit more, you can see the where we have, so the solid line again is the function itself, where we have peaks or troughs is where we'll have on the dashed line your 0 points, right, crossing the x-axis right here, which you would expect. The frequency is changing at the same rate, and then it's looking at the rate change of the frequency. That's your 2x here. So from this conceptual perspective, this does make sense too. And we can see how we can apply the chain rule. Now the next thing I want you to do is look at how we're going to apply a chain rule in combination with an additive rule that we looked at in previous video in this series. Okay, so here we have sine squared plus cosine squared. Well, we know from a trig function, so this is one of the fundamental trig functions that I remember because it shows up a lot. Sine squared plus cosine squared is just equal to 1. So I can take the derivative of 1. That's easy. That's a constant. So that's going to be just 0. But I don't know the derivative of sine squared, and I don't know the derivative of cosine squared. So I can solve for these individually using the chain rule. So this one's a little bit trickier, right? So take a second and see if can you think of what substitution, either through u, or what's an internal function and an external function. This one is not as apparent as the 3 other examples that we just did. All right, so take a second, try to think about it. If you need more time, press pause. Okay, so the way I approach this problem is I see a squared. Well, the only time I've used a square in my derivatives is in the polynomial. So I can treat this as my substitution, the square component. So I can think of the sine and cosine as my inner function and squaring this inner function as my outer function. So my inner functions, I will have 2 because I have 2 terms here. I'll have sine of x and cosine of x. So I'll have a u1 and u2 or a g1 and a g2. And my external function is going to be the same for both of them, so I just use 1, just x squared. So if I plug in u1 squared or u2 squared, I'll get the sine squared or cosine squared in the full function. So if we graph these, let's see, I have my sine x in orange, my cosine x in purple, and then when we square it, there's nothing that's going to be below the x-axis, right? So sine squared in blue, can you see it? Yeah, right there. And then cosine squared in green, you can see it there, right? It's just going from 0 to 1, right, for those, which makes sense. And then in this dotted red line, I have my x squared function, and my full function is sine squared plus cosine squared, or just 1, right? So it's going to be a constant. Okay. So what we need to do now is we're going to take the derivative of u1 and u2 with respect to x, and then derivative of f of x with respect to x, and then we'll do a substitution where we use dy du and then substitute the u terms, right? u1 and u2. So we'll see that in a second. So derivative of sine of x is going to give me cosine. Derivative of cosine is going to give me negative sine, and we see that right here. Derivative of x squared is just 2x. Okay, so we can look at it in this form here, right? So derivative of u1 squared, that's my y term here, right? That's basically the x squared du1 with respect to u1, or with respect to sine x when we do final substitution, times the derivative, right, du dx, or the du1 dx. That's d sine x dx. That's cosine x. And then similarly, du2 squared, right, cosine squared term with that substitution, du2 times d cosine x dx, and that's going to give me negative sine x. Okay, so this du1 squared du1, that's just the same thing as derivative of x squared. So this will be 2u1, right? This will be 2u2, and then my cosine and my negative sine x. And then I'll just do my substitution. To substitute a u1, which is just sine x, substitute my u2, which is just cosine x. So I got 2 sine x, right, with that u1 substitution, times cosine x. This essentially is the derivative of sine squared x. Then substitution here, u2, 2 times cosine x, right, that's right there, times negative sine x, or minus 2 cosine x sine x. This right here is the derivative of cosine squared x. So adding these two terms together gives me 0 as I expect. When we graph these, all right, let's see what we're going to look at. We have 2x in this dash, or this dotted red line here, the f prime, and the bold dashed line along the x-axis. That's my 0. That's my solution. All right, what else did I graph here? I have cosine x in blue right there, right, with a 1 value on the y-axis. I have negative sine x in green right there. And did I plot 2? Oh no, I mentioned that, right? I plot 2x there. Then I have 2 sine x cosine x in orange as an amplitude of 1, right? Going from -1 to +1. And it is 2 times the frequency as this blue line here, which is my cosine x. And then -2 cosine x sine x is just that mirrored. If you look at your trig functions, 2 sine x cosine x, I believe, is sine 2x. So it makes sense that the frequency is increased there. So you see these trig functions show up, or trig identities show up, but you don't need to memorize it. You can still derive this all without that. Okay, and this one's not interesting at all, right? The function itself is 1. The derivative of that is going to be 0. But this gives us a very good example of applying chain rule for something that has additive properties. All right, we can have all the additive properties. Chain rule can be applied to individual terms in the additive or subtractive system. So the next video we'll look at is the product rule. Here we have a function within another function. When we look at the product rule, we have a function multiplying by a function. And then the last thing we'll do in a couple videos is the quotient rule, where a function divides by another function. And really, you have a lot of power with the additive, the subtractive, here with the chain rule, and in the future, product and quotient rule, and all these trig and polynomial and exponential and natural log derivative properties. You have the power to solve a large variety of derivative problems. So we'll take a look at the next couple of videos, and with this short example, these short series of examples, hopefully you feel more confident in solving these problems.